Today I'm going to talk about measuring alternating current. In the previous videos I talked about the shape and other parameters of the alternating current. I told you we have our peak voltage, our peak-to-peak voltage, our RMS voltage, our period, our degrees of our complete cycle, and all those things. Well, how do we measure these? Well, the most common way we measure alternating current is with a simple AC voltmeter. Now, I use these little dodgy meters that they have at Harbor Freight for an important reason. I want you to know that you don't need to spend a lot of money to learn electronics technology. So they sometimes give these away, and whenever they do, I go get one. I have a ton of these, and I use them all the time, and I compare them to each other, and they don't always agree, but they're only off by a few tenths of a volt, and they work. Yes, if I'm going to do some real serious work in the field, I'm going to get some better meters. Not going to get a $7 or free Harbor Freight one. I have some other meters. I don't use them on camera because I want you to see that you don't need to spend a lot of money. When I get to oscilloscopes, yes, I will show you my old-timey analog oscilloscope because I like to use that to demonstrate how to use an oscilloscope so you learn what it means. But when I measure things in the projects or other ways in the class, I'm using a little $25 oscilloscope you can get on Amazon for around $25 because I want you to know you don't have to spend $1,500 on an oscilloscope just to learn how to use one. So I use the little cheap dodgy things. Yes, I have more expensive oscilloscopes, so you'll see my old-timey analog scope, which I really like using for my oscilloscope video, but keep it cheap because I want you to know you don't have to spend a lot of money to do this. So here we have my cheap little meter, and it works just the same as the more expensive ones. It's just a little dodgy. In fact, I think it appears that they use the battery as a voltage reference in these because as the battery ages, the voltage readings tend to go up. Oh my gosh, that's cheap. Can't even afford a little voltage reference. If I'm right about that, maybe the newer ones aren't so bad, but I've had some of these that as the battery goes down, the readings go up. But anyway, they have DC volts, resistance, even has a little transistor HFE tester. I never used that. DC amps, the high amp measurement. But for AC, what we're interested in is just these two little guys right up here. Let's even put this up to the camera. Right there is AC. It's 750 volts and 200 volts. And that's what we use for measuring AC. So what kind of AC measurement do I get? Well, it says, what does it say there? It says ACV. So if it doesn't qualify it, it's going to be RMS. So this measures the RMS voltage of a sine wave. And I said a sine wave because it's the way it measures only works accurately with a sine wave. What it does is it takes our sine wave and it takes the peak voltage, whatever that is. Remember, here in North America, it's 170 volts. And it runs that peak voltage through a voltage divider. And it runs it through a rectifier and a voltage divider, and eventually in a capacitor too to smooth it off. And eventually goes to a DC voltmeter, and it says, okay, if that's 170 volts, that must be 120 volts. So it has the proper, I'm not going to do the math here because I could, but it's, 170 volts to 120 volts. So 50 volts difference there. And so it takes the AC, converts it to DC, runs it through a voltage divider, and then gives you that voltage. So the voltage is estimated knowing what the RMS of a sine wave would be. So just for what it's worth, for a sine wave only, the RMS equals our peak voltage times 0.707. So that's the formula they're using to derive the RMS voltage from the sine wave. But this only works for a sine wave. If I put a square wave on there, it's going to give me the same thing. If the square wave peaks at 170 volts, it's going to say it's 120 volts. But yet that has a lot more energy in it because it stays at 170 volts and it goes to minus 170. So the RMS would not be the same. So triangle wave, sawtooth wave would also have the wrong readings. But 99.9 times out of 100 when we're measuring our AC, it's going to be a sine wave. So this meter works just fine estimating it by basically using that bit of a formula there. And for what it's worth, if you know your RMS, your peak voltage, equals your RMS voltage times 1.414, which, by the way, is the square root of 2. Don't know if that's just a coincidence or if it's the way it works, but 1.414 is the square root of 2, so you multiply your RMS voltage by the square root of 2 and you get your peak voltage. So that's basically what that does. Now, you might pick up an AC meter and you see something on there. In fact, this is much more common than it used to be, because now with modern digital electronics, it's fairly easy to make a meter that can measure your true RMS without getting too complicated about it. And so if it says true RMS, that means it'll give you an RMS voltage no matter what the wave shape is. If it doesn't say true RMS, it's only accurate for sine waves. True RMS meters used to use a little heater wire or something like that, and they measure the temperature of the wire. So put an AC across it, put this across it, and you get so much temperature. Put 120 volts DC across it, you get the same temperature. And so they would measure RMS voltage that way. But modern digital electronics can do it a lot easier. So true RMS meters aren't as uncommon as they once were. But how often do we need them? Not very often, because almost always we're measuring sine waves. So that's using a meter. Okay, so how's the other way to measure this? And that would be with a time domain voltimeter. Yeah, I told you what that was already. That's just a fancy name for an oscilloscope. So what do we have on an oscilloscope is a screen. I'm not going to go into a lot of details about the oscilloscope because I do in a video down the road, but we have a screen, and remember we talked about the time domain. Horizontal is time, and vertical is volts. So it's a time domain voltmeter. And using it's a little tricky because we use a voltmeter, whether it's an analog or a digital voltmeter, we just have a nice little screen there that says how many volts it is. Analog meter is a little tricky to use. We talk about that in the DC class. Digital meter is pretty quick. Set it up for the reading, tells you the volts. Oscilloscope's a little different because the way it works is we have in the old timey analog scopes, we have an electron beam shooting out a screen. Modern ones simply use an LCD, but it's the same principle. We just have a little spot that goes across the screen. It takes a certain amount of time to go across there. And so as time goes by, that spot goes by. And at the same time, our voltage input makes the spot go either vertical or either go up or down. So if it goes up, it's more positive. And if it goes down, it's more negative. So higher voltage, lower voltage. So as time goes by, the voltage goes up or down or whatever. So let's put a sine wave across here. So as time goes by, the voltage goes up, the voltage goes up, the voltage goes up, then the voltage goes down and back up again. And so our oscilloscope, as time goes by, displays what the spot does. And in the video where I talk in details, I slow it way down at first, but normally we're looking at that, and this is taking, in most of the world that would be 20 milliseconds. So it's happening pretty fast, but you just see the picture and well, I know that took 20 milliseconds. You can't see it happen in real time because it's just happening too fast. So anyway, we have time this way and voltage that way. Once again, the oscilloscope is not as straightforward as a voltmeter because there's no numbers on here to tell you what everything means. But what we have to do is we have to set it for how many volts we want. So we have a knob that says, volts per division. So there's some lines across here. And we say, okay, I want that to be 5 volts from there to there. So I set this to a little knob and put that to 5 volts. And the time, let's say I want, how about I want 20 milliseconds from there to there. Okay, that's going to be 20, 10, that's going to be 5 milliseconds. 5 and 5. So each horizontal line, each vertical line is 5 milliseconds later than the previous one, and each horizontal line going up is more positive, going down is more negative by 5 volts. So I'd set those knobs like that, and then I have some other knobs that move my beam up and down, so I can, okay, let's make this 0. So I move it up and down so that my beam is right there. So there's my 0. So let's run my wall power through a transformer, transforms it down to, let's say, about 7-volt transformer, and that's going to take that up to about 10 volts up, about 10 volts down, 10 volts up, 10 volts down. How did this get to be 0? I turned a knob until that's where it was. And so it's a little tricky, and once again, I go into much better detail in another video, but we set it up, and then we can get a picture of our wave. So now that we've got that picture, we can measure, well, what's the peak voltage? Well, that's 0 because if I have another control here somewhere. I can switch it over here and GND. In other words, makes that line 0 volts. So I push this to GND, that becomes a straight line. I move it up and down and say, okay, I want 0 to be right there. Then I flip this back up to either DC or AC. I'll talk about what those mean later. And then I see my wave on there, and I can see, well, see, there's my 0. So that's 5, that's 10 volts. That's -5, that's -10 volts. And so that would be, okay, 10 volts peak would be the same as about 7.07 volts RMS. And so I can make that measurement. So I can see my peak voltage, I can see my peak to peak voltage, and I can calculate my RMS by taking my peak voltage, which, okay, that's 0 volts, 5, 10. Why is that 10 volts? Because I said I want each line to be 5 volts apart. Why is that 0? Because I turned a knob that made that 0. And so it goes from 0 to 10 volts. So I have 10 volts peak, multiply that times 0.707 equals about 7.07 volts RMS. So that's how I do an RMS measurement on an oscilloscope. So you can see why we often use peak and peak-to-peak voltages with an oscilloscope, because we don't have to do any conversion. So this will give me my RMS voltage. The oscilloscope gives me a picture of how the voltage changes over time, so I can see the peak voltage and then use that or calculate my RMS voltage. But the other thing we can measure with the oscilloscope is the time, because what is this? It's time. This is 5, 10, 15, 20 milliseconds. It's 5, 10. Looks, got that a little bit off, don't I? So if I want to draw this right, let me try redrawing that wave in there. Let's see, it should peak there, 0 there, peak there. There we go. Okay, I'll just leave it the way it is. So 5, 10, 15, 20 milliseconds. I do one complete cycle in most of the world, so it's 50 cycles per second. So now that I have that, well, hey, this is 5, 10, 15, 20 milliseconds. So I can tell you how long it takes to complete one cycle. And if I know that, I can tell the frequency, because my frequency, I'm running out of room to write stuff here. My frequency is equal to the reciprocal of my period. So my period is 20 milliseconds. Take the reciprocal, and I get, well, in this case, 20 milliseconds, I get 50 hertz, 50 cycles per second. And also my period is equal to 1 over the frequency. And so that would be 20 milliseconds there. So the reciprocals of each other. So I can also measure the time. And if I have a dual trace oscilloscope, I can actually put 2 traces on there. And here I have 2 sine waves that are, well, that's there and that's there. Looks like they're 90 degrees apart. So I'm seeing that they're 5 milliseconds are peaking 5 milliseconds apart, which happens to be 90 degrees. And so I can actually measure my phase with an oscilloscope too. It's a little tricky because you have to compare one to the other. But I can see that's crossing 0 there, that's crossing 0 there. And it looks like it's under the peak, so that's 90 degrees apart. So I can also use an oscilloscope, a dual trace oscilloscope, to measure my phase. So anyway, that's just a quick overview of measuring AC. One we can measure with a meter, which is probably the easiest way to do it. Just gives us an RMS voltage. And this one can measure up to 200 volts. Other meters can go higher. Or we can measure with an oscilloscope, which actually gives us a picture of what the voltage is doing over time. It's a little tricky to set up. I gave you a quick overview here, but the next video is going to go into much more detail on measuring with an oscilloscope. If you found this video useful and informative, please give me a thumbs up down below. It really helps the channel. And subscribe, because that not only informs you when I put new videos up, but it really helps the channel also. And a big thank you to my patrons at Patreon. I could not make these videos without your support. If you want to help me put these videos online and keep real vocational education free at vocatomy.net, you can go to patreon.com/join/vocatomy and pledge your support. And again, a big thank you to my patrons who make this possible, and a big thank you to everyone for watching.